What the L stand for?
It's an I. Change font. Not Arial. Let me give it Times New Roman or something. Okay, so that's an I, and I is current. So V is voltage. I is current. R is resistance. And Ohm's law tells you that voltage is equal to current times resistance. So in terms of the number, I put in what I knew. I knew two things. I knew the V and I knew the R because I set them up. And then I want to solve for the current. I'm also measuring the current in the simulator, but I want to see that what I think and what the simulation thinks agree. I want them to be a check on each other. And so I divided, numerically, I divided 12 by 169. Now I have to worry about units. This is supposed to, it's a simulation. It's not a real physical measurement, but it is supposed to correspond to a physical measurement. And physical measurements typically come in units. Every once in a while, we have like what we measure as a ratio or something like that. But mostly we measure things that have some unit. And so we have to figure out the units. So I'm dividing volts by kiloohms. If I divided a volt by an ohm, that would give me an amp. But I'm not dividing a volt by an ohm. I'm dividing a volt by a kiloohm. Kilo is big, 1,000 big. And so when I divide by 1,000, I'm going to get thousandths. And so my answer is going to be in milliamps. So if I divide volts by kiloohms, I get milliamps. And then if you come back over here to the simulation, in the ammeter, you see there's this little M here. Okay, and then the A. So it knows, it puts the A over here. It's an ammeter. It knows it's going to be measuring in amps. And so it gives you the A out here sort of built in. It doesn't know when we start simulating whether the current is going to be large or small. And so it doesn't know if it's milliamps ahead of time. And that's sort of why it's putting the milliamp in the display, because that could change. Sometimes we'll get amps, sometimes we'll get milliamps, sometimes we'll get microamps. And so you've got to watch these, this little prefix here to make sure you give me the right one. Any questions so far? All right. Now let's try now series. So let's have two resistors and put them in series. So I'm going to add another resistor to this circuit. Resistors in series, being in series means that you experience the same current. So let me do insert page break. That's not what yeah, that's okay. Okay, so series means same current. Okay. So what does that mean here in the, all right. So I have this battery. The battery has the ability to push charges out on this side and then have them come around to the other side. It supplies those charges with some energy, and then they leave this side with that energy. They use up their energy along the way, and then they come back home, having used up the energy. So they're less energetic when they get home, like me. Okay, so right now I do have two things in series. The resistor and the ammeter are in series because they see the same current. The current comes out of the top, it goes through the 1.69, it goes through the wire, it goes through the ammeter, and then it continues on down to the back to the other side of the battery. There's no wire here for it to go someplace else. The only place it has to go, it starts here, it goes through the R1, it goes through the ammeter, it comes back to the other side of the battery. It's got no place to go other, so it's all the same current. The battery is happy to send charges out, provided that you give charges back. Okay, you've used something with a battery and the batteries have run out, and then you've had to change the battery.
So the amp is acting as an alternator.
Say it again.
Is the amp acting as an alternator?
Alternator. I'm going to say no.
So how the battery get it charge back?
Because it leaves one side and comes in the other. It's got to, the charge has got to leave one side and come back into the other. There's got to be a circuit. There's got to be a circle, a closed path. Otherwise, we've got a problem. If charges left, and only charges of one type, we've got positive charges, we've got negative charges. If charges of one type left the top end of the battery and went someplace else, then the battery would have, now we say the battery's charged. When we say the battery's charged, we mean that it has energy, not that it has more positive charges than negative charges. So you've got to watch like the common language. So like, you ask like, is your car battery, is it charged? What you're saying there is, does it have energy? Can it do something for me? But in a physics class, when we say is something charged, we mean it has more positive charges than negative charges. That's not what we mean in like the outside world. Outside of this class, if you say, is the battery charged, we mean, does it have energy? Inside this class, if we say something's charged, we say that it has more positive charges than negative charges, or vice versa. So we don't want the battery to be physics class charged. That would be bad. Like you've got a calculator, you've got a smoke alarm, whatever you have a battery for, and you've had to change that battery. If you had a like physics class charge situation, if it had more positive charges than negative charges, then when you went to change the battery, it would give you a shock. Things that, if there's more positive charge on something than negative charge on something, or vice versa, and you touch it, it doesn't like that situation, and it's going to give you a shock. For a battery to be charged, when the battery is charged using the words like outside of physics class to say it's charged, meaning it has energy, it's not going to give you a shock. It would give you a shock if you were part of the path connecting the one side of the battery to the negative side of the battery. If you're completing the circuit, there's always some damn fool, and it's always a guy. You give him a battery and he wants to like lick it or something like that. Okay, and then it will shock you because you are providing something that conducts electricity from one side to the other. Then you're part of the circuit, which you don't want to be. Okay. So anyway, But again, so whatever left on the one side had to come back on the other side because we don't want our battery to shock us when we have to change it. So, so all those charges are going to leave. What really moves in the real world tends to be the negative charges, but what we always talk about in science classes is the positive charges. It's just a convention. So if I talk about positive charges going around clockwise, what's really happening is probably electrons going around counterclockwise. But the convention is we talk about positive charges, and that's due to Benjamin Franklin. So if you want to be grumpy, go like yell at a statue or something. Okay, so some positive charges leave. It's got to go through the resistor. Positive, just to have some pileup of positive charges again is not a good situation. It's very, it costs a lot of energy, and also it will shock you. So those positive charges are not going to stay anywhere. They're going to leave, they're going to go through. Currents move, charges moving is a current, so they're going to move through here. So this has a current. They're going to move through here. To say there's no place to go. They're not going to accumulate anywhere. They're going to move through here. This happens to have the ability to measure that current. So there we see the measurement of that current. And then they can carry on and complete the circuit. Okay. So if two things see the same current, they are said to be in series. So right now, the resistor R1 and the ammeter are in series. But the ammeter is supposed to be ideal. It's supposed to like give you a measurement and not do anything else, not change anything. So that's why when we did our calculation, we found 7.1. The ammeter measured something, but really didn't change anything. It's not quite true, but it's in the ideal world, that's true. So now, are the battery and the ammeter in series? Well, yes, we don't often talk about the battery being in series. We talk about the battery as the source of the current that goes through the other things. But yes, strictly speaking, a current can be thought to move through the battery, and it is the same current. So we usually think of it as the beginning and the end of the current, and we don't tend to talk about it. But strictly speaking, yes, it would be in series. Okay, so let me add, with this definition of series, meaning that they see the same current, I'm going to add another resistor. So here's the 169. I'm going to break the circuit. Do I have it off? I have it off. I'm going to break the circuit. I'm going to add another resistor of, I don't know, 3.16. That sounds like a good resistor. Put it in there. Close that guy. Okay. So now, I'm coming out of the battery. The charge is not going to accumulate anywhere. It goes through R1. It's not going to accumulate anywhere. It goes through R2. It's not going to accumulate anywhere. It goes through the ammeter, and then it goes to the other side of the battery, so the battery doesn't shock us when we have to change it. Okay. Now you see that 7 didn't change, but that's because I have not rerun the simulation. This is not right. It doesn't clear, the system doesn't clear out, doesn't say like, oh, you made a new circuit, let me clear out the ammeter reading. It doesn't do that. So it can show you, this is not the right answer. Let's rerun the simulation. Okay, so now we have less current. Okay. So we have, let me know, let's do it this way. Okay, so we have the two resistors. They see the same current. Current has no place else to go. Current comes here, goes through R1, must go through R2, must go through the ammeter. All those three things are in series, no place else to go. And that's what we mean by series. Now the voltage is like the energy to be used up. Strictly speaking, the energy per charge. So each charge has some energy. We talk about the energy per charge, or for each charge, if you will. And that's this thing, 12 volts. And the 12 volts has to be, this side's got to be 12, and this side's got to be 0.
So the resistance are what, like transistors?
Say again?
The resistance are what, like transistors or what?
We're not ready for transistors. We're going to turn that statement around by the end of the course. And we're going to say that a transistor, the word transistor sort of is a combination of the word transfer and resistance. So you're way ahead on talking about transistors, but transistors are something that can change their resistance. These right now are simple resistors, and they just they have one resistance, and that's that. They can't change it. So transistors and resistors are related. We're starting with the simpler thing. We're going to get to transistors, but it's going to take us, like, I don't know, 8 weeks or something. So what is a resistor? A resistor is something that can use up some of your energy. What is that useful? I mean, sometimes when we get to transistors and diodes, one thing we'll learn is they don't like to have too much current, because that will fry. A resistor is kind of a robust thing, whereas a transistor or a diode is a more delicate thing. They're more useful, but they're more delicate. And so sometimes one of the jobs of a resistor is to sort of protect the more delicate things, to sort of take the brunt of anything. So like say I have that transistor and I put it in its low resistance mode, that might give me too big of a current and fry the system. But if I have a resistor in there, it will take the brunt and save my system from frying. So that resistors kind of take up some energy. We've got this energy, we've got to use it up. And that's what sort of resistors do, is they resist the current, they make you use up some of your energy. And you say, why do I want to use up my energy? Well, I want to use up my energy there rather than in the delicate part of my system to protect the delicate part of my system. When else might I just want, here's a circuit where you just have a resistor for the sake of resistor. You use up resistors use up energy. That's what I said, they use up energy, and they must convert that energy into something else. Typically, it's heat. So the resistor will use up the energy and convert it into heat. So if you like toast in the morning, then you're using a resistor because you've sent some energy through a resistor. That energy is given off as heat and it toasts your bread. Not these lights so much, but incandescent lights are just a simple resistor. And you send some current through the resistor of an incandescent light bulb, an old-fashioned light bulb, and it gets hot enough. So it's giving off so much heat that the heat becomes visible. The toaster becomes a little bit visible, and then it sort of maybe becomes orange. The light bulb the wire's not as thick, but it's actually what wire there is hotter. And so then that light becomes, it's a higher temperature, and therefore it becomes like white light. Okay. So those are situations where you might just have a resistor for the sake of having a resistor, a light, a toaster, or a light bulb, or something like that. And other times they're protecting other things. Okay. So we said, what does a resistor do? It uses up some of our energy, or energy per charge. It uses up our voltage. And I have 12 volts to use up. And I use some of it in the 3, some of it, where the hell did I get a 3? I use up some of my 12 volts here and some of my 12 volts there. I have 12 volts to use up through the course to get from one side of the battery to the other side of the battery. I have 12 volts. I must use it all up. I can't use any more up. I can't use any less up. I have to use the whole 12 volts and nothing but the 12 volts. Okay. So some of the 12 volts is here and some of it's here. So that's V1 plus V2 is going to be equal to the 12. I have to use up all of it. Both of the resistors, being resistors, obey Ohm's law. So I would say V1 is R1 times I1 and plus R2 times I2. So here's just V1 is this. So I don't know, let me make it a color or something like that. Make this orange, why not? And then this is the corresponding orange. So V1 is R1 times I1. Let me switch to Times New Roman again, so the I's look like I's. And the same thing for 2. But we said this is series. Our whole definition of series is that those currents are the same. So I1 and I2 are the same, and I'm just going to call them I. And then I can factor out. Let me do it this way. Control, copy, Control V, there we go. I'm going to factor out an I, like that. Okay. So now I have it, then it looks like it's 1 R times an I. I have, in my parentheses, I am adding 2 resistors, and I multiply it by a current. So that still looks like Ohm's law. Still looks like a resistance times a current is giving my voltage of 12. And so we call this an equivalent resistance. We say if we add those 2 resistances, that one resistor would have the effect of those 2 resistors. What am I doing? Oh, I'm running. I don't want to run. So I'm going to copy this circuit. I'm going to paste it down here. That's not what I wanted to paste. Can't seem to delete it. There. It doesn't want to go. All right. There, I'm copying it.
It's running.
It's running? I thought I turned it off. I did not turn it off. Thank you. I thought I turned it off. That's why nothing was working. All right. There. Okay. Now I've made a copy of the circuit, but I want to do this. I want to do R1 plus R2. So that is what? 1.69 plus 3.16, and that is 3.85. So this idea is that if that doesn't seem right. Oh, I missed a 1. So 1.69 plus 3.16. That seems better, 4.85. So the idea is if I take the 2 resistors, replace them with 1 resistor that has the resistance of 4.85, it should have the same effect. So I'm going to take 4 out of the picture, rejoin the circuit, and then I'm going to right-click on this guy and change him, keep the K, I want the K, but make this 4.85. And now I have 2 circuits that are supposed to be equivalent. I'm going to run them both. And they have, for the same voltage, they give you the same current. So these 2 resistors in series, R1 and R2 are in series. They see the same current of 2.47 milliamps. I can replace those 2 resistors with 1 resistor. So here's where I come into the combination. Here's where I go out of the combination. So I replace the 2 resistors with 1. And here's where I came into the combination, and here's where I come out of the combination. And it has the same effect. For the same voltage, it gives me the same current. That's the idea of equivalent resistance for resistors in series. Any questions?
It's better to have like a multiple resistor or low voltage than one given.
Okay, so in terms of the voltage and the current they see, it's equivalent. What's not equivalent is the power. So power is, since you asked, you're getting a little bit ahead of me, but you're not as far ahead of me as you were the last time when you talked about transistors. So power is voltage times current, and that comes in the unit known as watts. Okay. So while this concept of equivalent resistance is the same voltage current wise, that if I apply the same voltage of the 2 resistors, I get the same current as if I applied that voltage to the 1 equivalent resistor. So in that sense, it's equivalent. That's what we mean by equivalent. They're the same. But they're not the same power-wise. Overall, they may be the same power-wise, but individually. So like these sort of in series here, again, are sort of sharing the brunt. So that's what resistors do. They take the brunt of the energy in case you have some delicate stuff. But even the resistors have their limits. And so you might want 2 resistors instead of 1 because they will take less of the brunt.
And less heat, right?
Say again?
Less heat.
Strictly speaking, like heat per second. It's a matter of power. So the overall, I guess individually they'll generate heat, but it's more about power. So it's more like heat per second. But yeah, they'll each will be generating less heat. They'll have smaller wattages. So that's a reason why you might not want the equivalent. You might want the original 2 resistors. But in terms of volts giving currents, they're the same, but there are reasons like power considerations where they're different. So that's sort of like the why you might want these things in series. We want things in series because we need to understand what series is. And even for the guy I was talking to Nabu before the class and was asking me what's the purpose of this course, the concept of series and parallel is all through computing. I mean, it's a lot more in hardware than in software, but even in software, we have a concept of parallel computing. It's a very important concept these days. And that idea of things, and when you're seeing if something can be, put in parallel or not, there's some concept of like what part of it can be in parallel and what part of it has to be in series. And those concepts that we use in computer science come from electronics. That the concepts of series and parallel that you use are much older. Electronics wasn't always computers. There are other things that aren't necessarily programmable that radios and what have you that electronics do. So the electronics is an older concept. People went around zapping each other back in the Greeks, So those things have been around a while. But the concept, so the series and parallel, that idea sort of comes from electronics into programming, into software and such. So we need to know about series and parallel, not just why we might have series in the first place, but we just need to understand the concept of series, period. It's important to how we function. Okay. So if something like in programming, there's something called like serialization, and serial means you have to do one and then the other. It's like this following thing. You can't work on them at the same time. Okay, so that was series. Okay. Let's talk about now parallel. Parallel, okay. All right, so now I want to talk about two resistors in parallel. So I will take that away. I don't want that. Am I running again? I'm running again. So now I'm going to turn to the concept of parallel. So I'm going to make it and then talk about it. That was no good. I didn't want to do that. I'm going to move everything down. I highlighted everything and hit a couple arrow keys. Good. Okay. Okay. These two now are in parallel. Okay. So let's talk about the battery. The battery gives a charge, some energy. It wants to push it out the top of the battery, bring it back in the bottom of the battery, and you've got to use up all 12 volts before you come home. So you come out of the top, so a charge comes out of the top, and then it reaches this node. That little dot we'll refer to as a node or a junction. If you make the circuit right, you can often just have a junction arise naturally. But if you need a junction and you're not getting it from your circuit, there's a thing here called place and a junction. I can place a junction. And then I can connect things to it. Because that didn't make any sense, so I'm going to delete it right away. But I just want to show you that the way you were making the circuit somehow ends up that you need a junction that you just can't get to sort of form naturally, then you do place junction. Okay. Let me show you one more thing while I'm thinking about that. So here I place a junction. If I'm drawing some wire and I want to make a junction at the end, that's not necessarily connecting to anything, but I just want to make another junction, I double click. So if you need a junction you don't have, place junction. If you need a junction, just sort of you're drawing a wire and you want a junction at the end, double click. Okay. So now a current comes out of here, comes to this junction, comes to this node, comes to this fork in the road, and has to make a choice. It's either going to go through the 1.6 R1, or it's going to go through the 3.16 R2, and then carry on its way. I can make either choice. Each charge, a bunch of charges come out. Each charge can make its own decision. And some of them will make this decision, and some of them will make that decision. But whichever decision you make, you have to use up the 12 volts. They are, remember, that's one of our rules of this battery. So when we put in the battery in the first place, we said everything on this side was 12 volts. Down here, we said this thing connected to ground, everything was 0 volts. Our concept of an ammeter is that it's ideal and it doesn't do anything. So I have to think of this ammeter as if it were just a wire. So this is still 0 volts. So this side is 12 volts and this side is 0 volts. So whether I went through the 1.69 or the 3.16, either way, I had to use up my 12 volts. Okay, so here's where I will always say, like my little mantra for are things in parallel. If there's a wire connection on one side and a wire connection on the other side, and that could be the right side and the left side, it could be the top and the bottom, does it just connection of wire on one side, a connection of wire on the other side. That connection can be connected to other things. That's not what's important. What matters is that there's a connection on one side and a connection on the other side. With no other device. There's not a battery here. There's not another resistor here. R1, here's one side of R1 is connected to one side of R2, and the other side of R1 is connected to the other side of R2. They are in parallel. Okay. Some of the current, so they see the same voltage. Things in parallel see the same voltage. Because a wire means I have the same voltage on this side, and a wire means I have the same voltage on that side. And so things in parallel see the same voltage. So let me write down something. Connected by wire on both sides. See the same voltage. Okay. So I see the same, they see the same voltage, and they're connected by wire. So visually, you look for them to be the wire to be connected on both sides, and then you know what does that mean in terms of voltages and currents. It means they have the same voltage. So series, we have three main concepts: voltage. So we have Ohm's law. We have three main concepts: voltage and current and resistance. And series meant they had the same current, and voltage is the other one, means they have the same voltage. So these guys have the same voltage. And the current adds up. So some of the charges go through R1 and some of the charges go through R2, but all the charges had to go through either R1 and R2 or R2. And so they would not go through both. There is a push. The battery is pushing you from one side of the battery to the other. They want to be as efficient as possible to get home, use up their energy and come back to the circuit. So if a charge went this way, the charge is being pushed. When I say this side is 12 volts and this side is 0, voltage you should think of sort of as a push. So there's something pushing you along the way. So the voltage pushes the charges through the circuit. So there's the 12-volt battery is pushing a charge through R1 or through R2. If you started to go, if you went through R1 and you wanted to go through R2, then you'd have to start cycling around and go backwards. You'd be going against the push. They're pushing you this way, and if you wanted to go in any kind of a circle, you'd have to go the opposite direction. So you'd be going against the push. The push is pushing you sort of around the circuit from the top end of the battery to the bottom end of the battery. That's how you're being driven. That's how you're being pushed. That's the way you'll go. You have a choice in which path you'll go, but you won't go around in circles. Maybe at some low quantum mechanical level, that might happen a little bit, but we're not going to talk about that. We're doing classical electronics. So it's not a crazy idea, but at this level of electronics, it doesn't happen. We're just talking basically about push, and it drives you in one direction. So some of the charges go through R1, some of them go through R2. That adds up to all the charge. All the charge that comes out of the battery either goes to R1 or R2. And the voltages are all the same. So we're going to start with the, I'll say I total is equal to I1 plus I2. The current adds up. The total current is split up. It either goes through 1 or it goes through 2. And we just sort of talked, it's not going to go around in circles or anything else. So it's going to go through 1 or it's going to go through 2. That accounts for all the current. All these things obey Ohm's law. If I take Ohm's law, V equals IR, but I solve it for current. So let me scroll up. Here's our Ohm's law, V equals IR, but if I solve it for current, it's V over R. So this would be V over R is equal to, let's say, total is V1 over R1 plus V2 over R2. Current is V over I. We said that the total current is I1 plus I2. V over R, just replace all I's with V over R. And then what did we say? We said that this guy uses up to 12 volts and this guy uses up to 12 volts. So V1 is 12, V2 is 12, the total V is 12, all the V's are 12. And therefore I get to divide everybody by V, and that leaves me with the following. 1, so I've divided through my equation by V, all the V's were the same. Let me write that down. All V's were the same. So it's common. So just a normal algebra thing, divide through by the thing that's common. So I get rid of the V and all those terms. But the V was in the numerator, so I still have to have some numerator, so the numerator is now 1. And this is the equivalent resistance for resistors in parallel. And so I'm going to say resistors in parallel, add reciprocally. That's that 1 on. Okay. So we have the concept again of equivalent resistance. I can replace these 2 resistors with 1 resistor. And if I give it the right resistance, the equivalent resistance, it will have the same effect. Okay. So I'm going to first let me run this guy as it is. And there is the result. Pay attention that it has no M in this case. There was no M here. So this is 0.011 amp. Okay. So now I'm going to turn it off, copy it, paste. I'm going to make an equivalent. Okay. I'm going to replace the 2 resistors with 1. So there's my 1. But I have to do this math. This is the math of my replacement. In the equation, I have 3, I'll call it inverses or reciprocals, or 1-ons. Okay, so I'm going to do this on the calculator. The calculator has a 1 on X button. The equation has this 1 on feature. I have a calculator that has this 1 on feature. There are different ways to do this. You can do it any way you want. This is the way I do it. This is the way I'm going to teach you. But you can do it any way you know how and want to do it. But my equation has 3 1-ons. So I'm going to make sure when I'm using the calculator that I use the 1 on X button 3 times. Okay. So let me take try to have 3 things showing at once. Let's see if how good I am. All right. So resistor 1 was 1.69. So I put in 1.69, and then I want the reciprocal of it. Then I want to add, so I hit plus, 3.16 is the next resistor, but I want the reciprocal of it. That sort of told me that I want to perform an addition, but it didn't perform the addition. I hit equals to force it to do the addition. So you see up here, it doesn't tell me the answer, it just says that's what you mean, but you haven't done it. Now let's hit equals. Now it's actually done that calculation. But that was only 2 reciprocals. Our equation has 3 reciprocals. I damn well better give you 3 reciprocals or I'm not right. I need 1 more reciprocal. And there it is, 1.1011. Okay, I'm going to do it one more time. So I'm going to clear. I'm going to say I did 1.69 reciprocal plus 3.16 reciprocal equals reciprocal. And I'm getting 1.101. So let me take this R3, and the idea is that this is the equivalent resistance. If I take my R3 and change it to 1.101, then I will get the same current out of it. So I'm going to go to properties. I'm going to change it to 1.101. Okay. So here was the, oops, does that weird stuff sometimes. Come on. Stop it. Okay, so let me turn this on. And here I'm simulating the original circuit and the simulated circuit. If it would stay where I want it to stay. It is not staying where I want it to stay. There. No, there it goes again. Okay. So the two resistors on the top were in parallel. They were connected by wire on one side and wire on the other side. I played my reciprocal addition game, got the equivalent resistance, put in that equivalent resistance, and I have the same effect. For the same voltage of 12 volts, I got the same current. Okay, so that is the game with resistors, series, and parallel. Other questions? Any questions? All right. Any of you people chatting at me? No. Okay. So what do we have? 10 minutes, which is not much. So let me just do maybe another one of these, not try to do truth tables in here. Okay. Let me just start a new file. Now in lab 2, we keep it sort of simple and just do, oh, here's series or here's parallel or something. Maybe we have at most 3, and then we're going to sort of work our way up to more and more resistors. Let's do, I don't want to go that low. Let's maybe have 4. I don't know that we'll solve for anything, but we'll just sort of talk about series and parallel. Okay. Let me make something that's tricky. I like to be tricky sometimes. Here's me trying to be tricky. Okay. I should have ground. Okay. So I have, move this wire a little bit. Okay. So I have R1, R2, R3, R4, and we're asking the question, who's in series, who's in parallel? What can we, if we're going to play our equivalent resistance games, what are we doing? What can we do to replace it? I didn't see Casey before, now I see Casey, okay. Now again, so purposely trying to be tricky here. So sometimes people will look and see like, oh, R1 and R2, if they're sort of on the same level, oh, that's series. These are not in series, because series means the same current. Some charge will come out of 12 and come to this junction point, and some of it will go through R2, and some of it will go through R1, and then it will get back together. So R1 and R2 are not in series, they're actually in parallel. Here's a connection of wire on one side. Here's a connection of wire on the other side. So don't say like, oh, they're on the same horizontal or they're on the same vertical. That means they're in series. That's not what we mean by series. In electronics, it's always about connections. Series means that you come into one and you must go through it, and then you have no choice but to go through the other one, and that's that. This is not the case here. Okay, I have this guy running. Okay, so these are not, even though they're at that same level, they are not in series. They are actually in parallel. These two guys, people often want to think that parallel means geometrically parallel. So these two guys, if you were in geometry class, you would say, oh, this line and that line, those are parallel lines. That's not what we mean in electronics. It's about the concept of series, and parallel is about connections. It's always about connections, how things are connected. And so the current comes out of here, and some of it goes through 2, and some of it gets through 1, and then it recombines. It all goes through R2, and then it all goes through R4. So R3 and R4 see the same current. So these guys are in series. It's not about geometrically being in parallel. That's not what makes you parallel. Parallel in electronics class is about how you're connected. Series in electronics class is about how you are connected. Series means that you see the same current. It's got no place else to go. Parallel means there's a connection of wire on one side and a connection of wire on the other side, which ends up meaning that you see the same voltage.
So the ammeter?
I can do that, yeah. I was focusing on this idea of, don't be fooled about this. I'll put in an ammeter, why not? Oh, I have that. Let me make a, where do I want to put it? Where do you want to put this? You want to put it here, down here? Where do you want your ammeter? All right, you didn't answer fast enough. I'm going to put in 3 ammeters to show something else. Okay, so I'm going to delete that wire, and I'm going to have an ammeter there. Where is it? Indicators. I have an ammeter there. I'm going to have another ammeter down here and another ammeter here. Okay, I'm going to break these wires. I think I had, what did I have? I had a wire here and going there. And then I'm going to break this and put this here. Okay, this looks crazy. But I made it crazy on purpose, so now I'm regretting that. Okay, so I put in 3 ammeters. This ammeter, U1, is in series with R2. If a current came up here, if a current comes out of the battery, comes to this junction, and if it goes up, it's got to go through U1, and then it's got to go through R2. It's got no choice. So these U1 and R2 are in series. So this is an ammeter measuring R2's current. This ammeter down here is in series with R1. If I take the lower, if I hit the junction and I take the lower path, I have to go through R1, then I have to go through this ammeter. The ammeter can be before, the ammeter can be after, doesn't matter. So long as it's in series, that's what matters with ammeters, that they're in series. Doesn't matter whether they're before or after. Then the current combines and it goes through U3, which is in series with R3 and R4. And so what we see here, and this is something you'll have to do in lab 2, so not quite with these values, but something like this. We see that these 2 currents, this current in the upper branch and this current in the lower branch, add up to the total current. So the current comes out, it splits up, some of it goes this way, some of it goes that way, and then it adds all together and carries on all the way through. Okay, more current goes through the bottom, The 2.67 is a smaller resistance than up here, so more current. It's the easy way out. This is a smaller resistance, so more current will go through the smaller resistor than the bigger resistor. And now I'm pretty much out of time unless there's like a quick question. No. All right. Thanks for reminding me to record, but now I'm going to stop.